This conference will now be recorded.
Good morning, one and all. So, in our topic in this video, today we will cover multitasking. This is part of your unit 4. So, you know what is a process, what is a thread. So, the ability to execute multiple processes simultaneously is referred as multiple processing. And those systems which are capable of processing multiprocessing are called multiprocessor systems. These multiprocessor systems require multiple CPUs and they can execute multiple processes simultaneously. The ability of the operating system to have multiple programs in the memory and ready for execution is called multiprogramming. Multitasking is referring to the ability of an OS to hold multiple processes in the memory and switch the processor from one process to another process. So you can just understand multitasking refers to the ability of an OS to hold multiple processes in the memory. So multitasking refers to the ability of an OS to hold multiple processes in the memory and switch the processor or the CPU from executing one process to another process. Your multitasking involves context switching, context saving, context retrieval. What is context switching? It refers to switching of execution context from task to another task. When a task or a process switches happens, the current context of execution should be saved to retrieve it at a later point of view, which is interrupted currently due to execution switching. So try to understand multitasking refers to execution of multiple processes in the memory by switching the CPU from one task to another task. And this multitasking is of three types: cooperative, preemptive, and non-preemptive. Cooperative multitasking means the CPU time is utilized for a process even if it is waiting for an IO resources. That CPU or the resources is not given to another task. Upon completion of one task, then only the CPU is given to another task. So that is cooperative. If it is not giving, it is called non-cooperative. Primitive means each and every task is given certain time allocation based upon time slot or priority, and each task or process is given independent chance to execute or utilize the CPU time. Non-preemptive multitasking means it is also same, but whenever one task is in the blocked state and waiting for an IO, the CPU resources is allocated to another task. So this is the difference. Determining which process or task is to be executed at a given point of time is known as scheduling. So we have to do task scheduling. Task scheduling purpose is it will decide which task or process is to be executed in which order. And this is done by task scheduling. What is the advantage of task scheduling is CPU utilization is utilized, is uh, CPU utilization is increased, throughput, the number of processes executed per unit of time will be more, and turnaround time, it is the amount of time taken by a process for its execution, will be less. Okay, so waiting time refers to amount of time spent by a process in being in the ready queue and waiting for the resources. Response time means it is the time elapsed between submission of a process and the first response. For a good scheduling algorithm, the response time should be as least as possible. For task scheduling, we have to maintain different queues. One is called job queue, which contains all the processes in the system. One is ready queue, which contains all the processes which are ready for execution and waiting for CPU to get their turn for execution. And the ready queue is empty when there is no process ready for running. And there is a device queue. It contains set of processes which are waiting for an IO device. So ready device queue contains set of processes which are waiting for IO device. Device queue contains set of processes which are waiting for an IO device. Ready queue contains all the processes which are ready for execution, waiting for CPU time. Job queue contains all the processes in the system. So scheduling means assign providing the CPU time for each of the tasks or processes, under which we are having non-preemptive scheduling. Under that, which one is first come first serve scheduling. So here, in order to allocate CPU time, we are using the technique called first come first serve. We are using the technique called first come first serve, non-preemptive. What is non-preemptive? A task will execute is under execution by utilizing a CPU time, and if it requires any IO device, the task will leave the CPU to be utilized by another task. So that is non-primitive. So if you see in this example, there are three processes P1, P2, P3, whose completion time is 10 milliseconds, 5 milliseconds, and 7 milliseconds. And you are have to calculate the waiting time and turnaround time for each process, as well as turnaround time and the average waiting time. So the sequence of execution of the process by CPU is represented by P1, P2, P3. Because P1 takes 10 milliseconds, and after that P2, because it is first come first serve. So next P2 it is 5 milliseconds. From 10 to 5 it is 15 milliseconds, and from there it is 7 milliseconds. So P3 will be completed at 22 milliseconds. So if you see the CPU time, the process is based called ready queue. So we are allocating CPU time to the process. We are allocating CPU time to the process based on the order in which they are in the ready queue. So based upon the scheduling technique, ready queue is maintained because it is first come first serve. First entered is P1, second enter is P2, next enter is P3. So allocation of CPU time to the process is based on the order in which allocating the CPU time to the process is based on the order in which they are in the ready queue. So once for every for a set of tasks to be executed, we have to make the ready queue based upon the scheduling algorithm. Here scheduling algorithm is FIFO, first in first out. So P1 is the first one which is entered into the queue. So that's why P1 does not require any waiting time. So it is 0 milliseconds. But P2 has to wait for P1 completion. So that's why it is 10 milliseconds. And waiting time for P3 is it is 10 plus 5, it is 15 milliseconds. The average waiting time you can calculate as total waiting time by divided by 3 process. It is 8.33 milliseconds. And turnaround time for P1 is 10 milliseconds, because turnaround time is time spent in the ready queue plus execution time. So time spent in the ready queue is 0 milliseconds plus execution time. Execution time for P1 is 10 milliseconds. So it is turnaround time for P1 it is 10 milliseconds. Turnaround time for P2 it is 15 milliseconds. Turnaround time for P3 it is 22 milliseconds. So average turnaround time is calculated by turnaround time of the three processes divided by 3. So it is 10 plus 15 plus 22, it is 15.66 milliseconds. For in the same non-preemptive scheduling, if you consider last come first serve technique, the ready queue is maintained based upon last in first out. And if for this example, the three processes P1, P2, and P3, P1, P1, P2, and P3, the estimated times of completion are given as 10 milliseconds, 5 milliseconds, and 7 milliseconds. P1, P1 it is 10 milliseconds. P2, P2 it is 5 milliseconds. So for P3 it is 7 milliseconds. So for non-preemptive scheduling based upon the last in first out, if you see the ready queue, it is P1, next P4, P3, P2. P1 is taking 10 seconds and P4 it is taking 6 milliseconds. So completion of P4 occurs at 16 milliseconds, completion of P3 occurs 23 milliseconds, completion of P2 occurs at 28 milliseconds. And the waiting time for P4 it is 5 milliseconds. Because the first one P1 is processed, it is 0 milliseconds. Waiting time for P3 is 16 milliseconds. And the average waiting time it is 11 milliseconds. And turnaround time for P1 it is 10 milliseconds. P4 it is 11 milliseconds. And P3 it is 23 milliseconds. Turnaround time for P2 is 28 milliseconds. Totally turnaround time, average turnaround time is calculated by turnaround time of all the process divided by 4, it is 18 milliseconds. So next is the third method, non-preemptive scheduling, shortest job first scheduling. A process where execution time is high, that will not be given CPU time, and that will be kept in the ready to in the last. So that is lead to starvation for long time. So based upon that, and this type of is done in Windows CE, which supports 250 levels of priority. And if you go for non-preemptive scheduling, another priority-based scheduling, here the priority is assigned to the task based on well its creation, and dynamically this priority will be changed. And this non-preemptive priority-based scheduler sorts the ready queue based on the priority and picks the process with the highest level of priority. So if you see the same example, three processes P1, P2, P3, execution times are 10, 5, and 7 milliseconds. And in between, you have one more yeah, um, and this process P1 must be completed in 10 milliseconds, P2 must be completed in 5 milliseconds, P3 must be completed in 7 milliseconds, but the priorities are 0, 3, 2. Means the priority for the first one is 0, and 0 is taken as highest priority, and 3 is the lowest priority. So the whenever the ready queue is maintained, it is based on priority based. So first one, the priority is P1, next priority is P3, next one it is P2, because P2 is having the value 3. 3 means it is having the lowest priority. So P1 it is 10 milliseconds. From 10 milliseconds, it is P3, it takes 7 milliseconds. So completion of P3 completes at 17 milliseconds. And from 17 milliseconds, it is P2, it is 22 milliseconds. So if you see the turnaround time for P1, it is 10 milliseconds. Turnaround time for P2, P3, it is 17 milliseconds. Turnaround time for P2, it is 22 milliseconds. And the average turnaround time will be 16.33 milliseconds. If you see the drawbacks, it is similar to SJF, shortest job scheduling, but non-preemptive priority-based algorithm possesses a drawback of starvation. Whenever a process whose priority is low may not get a chance to execute if more and more processes are occurring with high priority, and before the process with low priority gets its chance for execution. Starvation can be effectively tackled in priority-based non-preemptive scheduling, and a task which is preempted by scheduler is moved to the ready queue. And the next we'll see the preemptive scheduling. What is preemptive scheduling? Each tasks or process will be given a specific time slot based upon the priority or the time. And if you see the example, in this example, there are three processes P1 whose completion time requires 10 milliseconds, P2 requires 5 milliseconds, P3 requires 7 milliseconds, and one more process P4 it is entering into the ready queue with 2 milliseconds. So at the beginning, there are only three processes P1, P2, P3 available in the ready queue, but the SRT schedule picks up the process with the shortest remaining time for execution completion, and it is placing. So P1, P2 is taken with the 2 milliseconds, then it is P4, then it is P2, again P3 and P1. Like that, a ready queue is made, and each process in the ready queue is executed for a predefined time slot. Like that, waiting time for P1 is 14 milliseconds, Waiting time for all the average waiting time comes out to be 5.75 milliseconds. Turnaround time for P2 is 7 milliseconds. Turnaround time for P4 it is 2 milliseconds. Turnaround time for P3 it is 14 milliseconds. Turnaround time for P1 it is 24 milliseconds. And the average turnaround time is coming out to be 11.75 milliseconds. So you can also go for a round robin scheduling where process P1 execution switches to P2, P2 switches to P3, P3 switches to P4, and once P4 execution over, it is switching to P1. And this is one more example where round robin algorithm is implemented. P1, P2, P3, again P1, P2, P3. So each process is given exact time slice as 2 milliseconds, due to which the waiting time for P1 it is coming out to be 6 milliseconds. For P2 it is 6 milliseconds. For P3 it is 4 milliseconds. And the average waiting time is calculated as 5.33 milliseconds. And if you see the turnaround time for P1 it is 12 milliseconds, and for P2 it is 10 milliseconds, and turnaround time for P3 it is 6 milliseconds. Average turnaround time is nothing but sum of the turnaround times of the three process divided by 3, it is 9.33 milliseconds. So preemptive scheduling, we can also go for priority based scheduling. So under priority based scheduling, we can see that there are three processes with P1, P2, P3 with estimated completion times of 10, 5, and 7 milliseconds. And here the priority is given as 1, 3, 2, means 0 is highest priority, 3 is the lowest priority. So once you prepare the ready queue, it is P1, P4, P1, P3, P2, they are entering with their completion times as 0 milliseconds. Then P4 it is 7 milliseconds, P1 it is 16 milliseconds, P3 it is 23 milliseconds, and P2 28 milliseconds. So you can create a ready queue for each scheduling algorithm based upon the algorithm logic, how it is designed. And this ready queue, if you see in this example, P1 with highest priority is kept in the scheduling, and now process P4 with estimated execution completion, time is 6 milliseconds. So after 5 milliseconds, 6, it is 11. So P4 completion time is shown as 11 milliseconds. So coming to the execution time, waiting time for P1 is 6 milliseconds. Waiting time for P4 it is 0 milliseconds. Waiting time for P3 it is 16 milliseconds. Waiting time for P2 it is 23 milliseconds. And corresponding turnaround time is also varying. For P1 it is 16 milliseconds. For P4 it is 6 milliseconds. And turnaround time it is 23 milliseconds. So average turnaround time it is 18.25 milliseconds. So if you see how to choose RTOS, the decision of an RTOS for an embedded design is very critical. A lot of factors needed to be analyzed carefully before making a decision on the selection of an RTOS. These factors can be either functional or non-functional. Under functional requirements, first we'll see the processor support. The RTOS requires read-only memory for holding the OS files, and it is normally stored in a non-volatile memory like flash memory. So it is not necessary that RTOS support all kind of processor architectures. It is essential to ensure that the processor support by the RTOS. And the next functional requirement which tells how to choose an RTOS is the memory requirement. The OS also requires working memory RAM for loading the OS service, and the embedded system is memory constrained. It is essential that minimal RAM and ROM are required for OS in their consideration. And the next parameter is real-time capabilities. It is mandatory that OS for all embedded systems need to be real-time in behavior, and the task scheduling policies plays an important role in real-time behavior. Kernel and interrupt latency. The kernel of the OS may disable interrupts while executing certain services. So for an embedded system, the response requirements are high and latency should be minimal. So inter-process communication and task synchronization. The implementation of IPC and synchronization is OS kernel dependent. So these are the functional requirements. Real-time capabilities must be there. Kernel must be response time must be high. Interrupt latence must be low. Inter-process communication and task synchronization must be done by the kernel. Modularization support. So most of the OS provides a bunch of features. It is very useful if the OS supports modularization, wherein the developer can choose the essential modules and recompile the OS image for functioning. So modularization support is also essential. That is also a functional requirement. And support for networking and communication. The OS kernel may provide stack implementation and driver support for a bunch of communication interfaces and networking. Ensure that OS under consideration provides support for all the interfaces required by the embedded product. Development language support. Certain OSs include runtime libraries required for running applications. The OS may include these components as built-in component. If not, check the availability of the same from a third party. Non-functional requirements. So these are the non-functional requirements for choosing an operating system. First one is custom developed or off the shelf. Next, it is possible to complete the development of OS as a custom based, or you can also use the off the shelf available OS, or the cost for buying the OS is also deciding the requirement for OS. And development and debugging availability is also is one parameter. Easy of utilization of RTOS compared to existing RTOS. And after the sales, there must be less bugs. Critical path updates, support for production issues must be analyzed thoroughly. Device drivers. Device driver is a software which is acting as a bridge between the OS and the hardware. The user applications talk to the OS kernel for all necessary information exchange, including communication with the hardware peripherals. So these are user level application tasks, A1, application 1, application 2, application 3. There is an OS which is separating from the hardware with the device driver. The architecture of OS kernel will not allow direct device access from the user application. All the devices related access should flow through the OS kernel, and the OS kernel routes it to the concerned hardware. So the OS kernel is routing these devices with the kernel, with the hardware. OS provides interfaces in the form of API, and your device driver abstracts the hardware from the user applications. These device drivers are responsible for initiating and managing the communication with the hardware peripherals. So drivers which come as part of OS is known as built-in drivers, and which are installed or communicating with are called installed drivers. For installed drivers, the driver is loaded on a need basis when it is required, and the device manager service of the OS is responsible for loading the device drivers and managing the drivers. And the underlying implementation of device driver is OS dependent. These device drivers can be run on a user space or a kernel space. If they are running in a user space, this is called user mode driver, and these drivers running in the kernel space are called kernel mode drivers. User mode drivers are safer than kernel mode drivers. If an error or exception is occurring, it will not affect the total kernel. If an exception are occurring in the kernel module, it may lead to the kernel crash. The way how a device driver is written and how the interrupts are handled in an OS, the device driver implements the following: device driver initialization and interrupt configuration. So a device driver will implement the following: device driver initialization and interrupt configuration, interrupt handling processing, client interfacing. Under interrupt handling and processing, it does three things. Client interfacing means interfacing with user applications. Basic interrupt configuration involves the following: you have to set the interrupt time type, whether edge triggered or level triggered interrupt, or you have to enable the interrupts, or you have to set the priorities. Next, the processor identifies an interrupt to IRQ. These IRQs are generated by the interrupt controllers, and a register, you have to register an interrupt service routine within an interrupt request. Whenever an interrupt occurs, depending on the priority, it must be serviced and the corresponding ISR must be invoked. The processing part of the interrupt is handled in an ISR. The whole interrupt processing can be done by the ISR itself or by invoking an interrupt service thread. The IST performs interrupt processing on behalf of ISR. It is always advised to use an IST for interrupt processing and to make the ISR compact and short. So in this topic, we have studied multitasking, how multitasking is done in the three methods called cooperative, non-preemptive, and preemptive. And this multitasking must be achieved by task scheduling. This task scheduling can be again done by preemptive and non-preemptive. And again, they are classified into first come, first serve, last in, first out, and shortest job, shortest remaining, and priority based. So after which we have seen in an example how we calculate the waiting time and turnaround time, and then we have seen how to choose an RTOS, for which there are functional requirements and non-functional requirements. Functional requirements are of 8 types, such as processor support, memory requirements, real-time capabilities, kernel and interrupt latency, inter-process communication, modernization support, support for networking and communication, development language support, whereas non-functional requirements are custom developed or off-the-shelf, cost, development and debugging tools availability, easy of use, and after sales. And then we have seen what is a device driver and how a device driver is saved in the memory, and how an OS kernel portion is providing interaction uh, to the hardware by the device drivers, and these device drivers will be stored in the user space or kernel space, and then they are going to implement the various parameters such as device initialization, interrupt configuration, interrupt handling and processing. So this covers our unit 4. So in this unit 4, we have seen what is an operating system and what are the types of operating system, what is a task, what is a process, what is multitasking, what is multiprocessing, what is multiprogramming, and what are the types of multitasking, and what is the task scheduling, what are the types of scheduling, and how to choose an RTOS. So this is all related to embedded firmware. Uh, so with this, I'll stop our class. We'll continue 15 minutes in a later video.